In this video, we're going to talk about Newton's three laws of motion. So Newton's first law is that an object at rest will stay at rest, and an object at motion will stay in motion unless acted upon by an unbalanced force. Okay, so basically this in simpler terms is just saying that things are going to keep doing what they're doing unless there's a force that changes that. Okay, so there's two examples here. This first one, this big rock that's just kind of sitting there, and these guys are standing next to it kind of precariously. This rock is at rest, right? So it wants to stay at rest unless there's a force that acts differently on it. So the forces that would be acting on this rock here would be gravity. Maybe the wind would blow against the rock a little bit. We have the force of the ground pushing up on the rock, right? All of these different forces, without getting into too much detail, those are the basic forces involved in this rock and its motion or lack thereof. So if we look at this rock, it's standing still. It wants to keep standing still unless there's a force that changes that. So if these guys here were maybe to push real hard on this rock, maybe they could get it to tip over, right? Because then they would be acting on it with a force. The same thing applies here. If we look at this guy, Marshawn Lynch, right? He's big running back, right? If he's coming down the field running towards you and you're trying to tackle him, you're going to have to put a pretty big force to change his motion, right? You've seen him kind of run over defenders before, right? Because he is going to keep his motion unless there's a force strong enough to change that, right? So if you want to tackle this guy who's running real fast, you have to put a force into him that's going to change his motion significantly. Okay, Newton's second law. Newton's second law says that the acceleration of an object, its motion, how its motion is changing, is going to depend on the force that you apply to it and also on the mass of the object. So however much force you put in and the mass of the object itself, those are the two factors that are going to influence the actual motion of the object or how much acceleration it's going to have. Okay, so the formula here is F equals ma, and technically this is the net force that we're applying to the object, so the total of all the forces involved. So the net force equals the mass times the acceleration. So basically we can think about this in kind of simple terms. The more force we put into something, the faster it's going to accelerate, right? If you push real slowly on an object, it might not move very fast, but if you push really hard, you can maybe shove it a distance and make it accelerate faster. So the more force you have, the greater the acceleration of the object is going to be. And the mass also influences this, because if you put the same force into a small object as you do into a big object, you're going to find it a lot easier to move the small object. The small object is going to accelerate at a much higher rate than the big object would if you put the same force into them. Okay, so we'll look at a couple of examples here of this. So if you want to pause the video and think about, we've got here a box filled with peeps, these little marshmallow peeps, if you've had those around Easter time. And we have a second box here filled with bowling balls. Okay, so we got the same guy putting the same amount of force into both boxes. One is filled with these fluffy little peeps, and the other is filled with these heavy bowling balls. How would the motion or the acceleration of the first box compare to that of the second box? Okay, so if you want to pause the video and think about this, but what's going to happen here is he's putting the same force into both of them. You can imagine this box is going to move a lot faster. It's going to accelerate a lot faster than this box with the bowling balls, which will be a lot harder to push because it's heavier. Okay, so the smaller the mass, the higher the acceleration is going to be if the force is the same. We'll say this is a force and this is the same force, and we'll say that these two forces are equal. Okay, so as long as the force is the same, the lower the mass, the higher the acceleration is going to be. Okay, and then the other thing we can consider here is how does the force influence this? So same thing, if you want to pause the video and think about this, we've got this guy pushing on this 100-kilogram box here, and we've got this giant guy pushing on the same box. What's going to happen when we compare the motion of these two boxes? If you want to pause the video and think about this, what's going to happen is we've got this guy, he's pushing the box along, right? And then this guy, assuming this is going to be a much bigger force than we have with a smaller normal-sized guy here, the bigger force is going to cause a much bigger acceleration. and the smaller force will cause a smaller acceleration. So the mass is the same here, right? We have these two masses, they are the same. The force is different. The bigger the force, the bigger the acceleration. So again, we talked about how if you shove something across the floor really hard, it's going to move a lot faster than if you push it slowly across the floor with a smaller force. Okay, so the bigger the force, the bigger the acceleration is going to be. Okay, and our last law of motion is Newton's third law. And Newton's third law basically just says that forces act in pairs. So for every action, there's an equal and opposite reaction. Maybe that rings a bell, maybe you heard that in middle school science. So basically, every force that is acting on an object, there's an equal and opposite force from the object. So this example down here of if you're kind of standing on a boat and you jump off to the side here, you can imagine the boat is going to actually go the other way because you're pushing on the boat pushes on you, and basically if you go this way, the boat has to go that way. Another example would be sitting in a chair. If we, let's say, tried to put a big chair under this guy here in the water somehow, assuming this chair was able to sit somehow on some surface or something down there, right? The guy's weight is pushing down on the chair, but the chair also pushes up on him, and that's what keeps him able to stand up. And we could also say the example of pushing on a wall. So let's say this guy, there's a wall here, and he pushes on it, right? He pushes on the wall, but the wall pushes back on him. So let's say he were to like run up to the wall. Let's say there was a wall over here, and he were to run up to it and jump into it. He could push off the wall, right? Because the wall is going to push on him as he pushes on the wall. So if you've ever tried that before, like jumping against a wall, if you've ever seen like parkour or anything like that, right? When you jump against the wall, you push on the wall with your legs, and then the wall pushes you off for every bit that you push into the wall. All right, so that's an example of Newton's third law as well. All right, thanks for watching this video on Newton's laws, and I'll see you in the next one.